Welcome to part 2 of advanced forecasting. So we are going to start off where we left at ACF and partial ACF. So these terms are important when you're talking about extracting information from the past. Why? Because autocorrelation is correlation between values of the same time series at two different times. So if you remember from your statistics class, you studied correlation. Correlation is a measure of the relationship between two variables like x and y. So you have two different variables and you can figure out whether they're related or not. In autocorrelation, auto suggests or informs you that the relationship is between y and y itself, the same variable. So if your variable y is a relation between y and y itself, or x and x itself. So obviously y is going to be related to y. So that's like, what are we talking about? Well, we're talking about values of y at a particular time being related to past values of y with a lag. So our values of y which are far apart by 1 week, are they related? So do sales of this week affect sales of next week, or say something or tell us something about sales of the next week? If you look about lag of 2, if you have weekly data, then you are saying, do sales that were 2 weeks ago, do they tell us something about the sales now? Okay. Then you can look at lag 3. Did sales 3 weeks ago tell us something about sales now? So if you look at the formula on the screen, you can look at the definition. You don't have to worry if you don't understand the mathematical equation, but I'm just going to explain some highlights. That you're looking at y at time t minus the mean, because correlation always looks at the difference from a mean. If you're above the mean, are you likely to be above the mean on the other variable? If you're below the mean, are you likely to be below the mean on the other variable? So that's just how correlation works. But think of the first term as yt. It's reflecting the level of yt, and you're multiplying it by the level of yt minus k. So if you remember the slide on notation, I said when you subtract from the time index, you're going in the past. So we're going in the past by k time periods, okay? And so we multiply that, and then we vary k, okay? For over the different possible values of k. And then we are kind of adjusting it by the variance of the y variable. A measure for the variance, not exactly variance, but it's like yt minus the mean squared. That's a measure of the variability in y to standardize the autocorrelation. So it takes value between +1 and -1. Okay, so we call it this variable r. So r of 1, if k is 1, then it means that correlation between y at any time t and y one time period prior, t minus 1, is r1. Okay. Similarly, you can find r2, r3 at different time lags, because yt versus yt minus 1, this is called lag of 1, because this is one time period in the past compared to this value. Okay. So autocorrelation, just like correlation, values lie between +1 and -1. Capital T is the length of your time series. So if you have 52 values, capital T will be 52. So if you want to know whether the autocorrelation is significant or not, you can compare it with ±1.96 times square root of the length of the time series. If your values are above plus the positive value or below the negative value, because autocorrelation can be negative, then they are significant at the 5% level. ACF is called the autocorrelation function. It's just a plot of autocorrelation values for different lags. So R1 followed by R2 followed by R3 followed by R4 and so on. And when you plot them, R1 is the first value, R2 is the second value, R3 is the third value. So you compute autocorrelation with lag 1, autocorrelation with lag 2, autocorrelation with lag 3, and so on. That's called the autocorrelation function. You don't have to do this manually. So you don't have to know the exact formula. But if a software allows you to calculate it, you can calculate it in software. Okay, so this is an example of the autocorrelation function for anti-diabetic drug sales in Australia. Okay, and you can see at the value of 0 there is no R value. Why? Because the correlation of Y with Y itself at a lag of 0 is just going to be 1 by definition. Y is correlated with itself by a value of 1, perfect correlation, right? But when you look at, so we don't plot that in an autocorrelation plot. When you look at here where the lag is 1, this is your R1. This has a value of about 0.8 something. So that's a pretty strong correlation. That means that if anti-diabetic drug sales are high for a particular month, they are likely to be high in the next month as well, right? So there's a relationship over time between Y values. So R2, when you have a 2-month lag, the relationship is weaker, but it's there, and R3 is weaker and there and slowly weakens over time. And then you see a spike at R12. That shows you that when you go back 12 months, you're in the same month of the last year. So if I am in March and I go back 12 months, I'm in March of last year. So the sales in March of this year are more related to sales in March of last year than they are to sales in February or April, the months around March of last year. Okay, so this is an indication of seasonality. Whenever you see the ACF function spike up at a lag of M could be 4 for quarterly data, 12 for monthly data, 7 for daily data, because weekly seasonality, that's an indication of seasonality. Excuse me. Right. So here we see at a spike, which is compared to the values next to it, is a little bit higher, and we would expect a similar spike at 2M. If M is 12, 2M is 24. So we go to 24, we see at the lag of 24, the value is higher than the values around it. And so this is evidence of seasonality. Every M lags, you see a little bit of a spike in the autocorrelation function. Okay. Now, if there is a lag at 1, if R1 is positive, let's say this is R1 is positive 0.8, R2 is going to be slightly less than positive as well. Why is that? Okay. Think about it this way. So R1, okay, let's say it's bigger than 0. Okay, so for example, this could be 0.8. Okay, that means that YT is related to YT minus 1, right? That's a lag of 1. But there's nothing about R1 that fixes the relationship to YT and YT minus 1. R1 is the relationship between any Y values which are 1 apart. So R1 being positive, 0.8, also means that YT minus 1 and YT minus 2 are correlated with 0.8. So this 0.8 applies to this relationship and also equally well to this relationship. Why? Because the lag is 1. Okay. Now what do we see? Well, YT is related to YT minus 1, and YT minus 1 is related to YT minus 2 by R1, just by R1. If only R1 was positive, not even looking at R2. So what that means is that YT is related to YT minus 2 through YT minus 1. But there is a relationship between YT and YT minus 2. So if there is a correlation at lag 1, this correlation itself will create a correlation at lag 2. So R1 being positive will tend to affect R2 to also be positive. Because the middle value, so you have this, this, this. So R1 means these two values are related. That's R1. R1 also means these two values are related. So this will create a relationship between this and this. And that will be R2. So R1 creates an R2 and an R3. So which is why this being significant is going to create correlation at R2, R3, R4. It's going to decrease because the more steps you have between two values, the more the relationship is weakening, but R1 is going to affect this. Now, there could be a unique relationship at lag 2 as well. And then what you observe here will be the unique relationship at lag 2 plus the effect of R1. Okay, you'll see that together. Okay. So often with ACF plots, you'll see this pattern where correlations at different lags go down slowly. So you'll never see R1 is positive and then you have 0 after that. Just R1 is positive by itself and R2, R3, R4 are all 0. You'll always see multiple autocorrelations being positive, and the magnitude would decrease. If it was a negative correlation, you'll see the negative magnitude also decrease. Sometimes it's sinusoidal. It goes down, then it flips to negative, then it goes back, and then it flips like that too. So you'll never see, well, you rarely, if ever, but almost never, you'll see the autocorrelation function just drop to 0. It'll always move down slowly, and then may spike up due to seasonality here, and seasonality here, but then it kind of has a decay. You'll see this, we call it decay. Okay, so you see this decay pattern in autocorrelation plots, and people don't like it. Why? Because when I look at this plot, I don't know if this value of R2, okay, how much of R2, this is R2, part of it is caused by R1, right? R1 is creating R2, but part of it also may be caused by our relationship between yt minus 2, or direct relationship, and yt. There may be a direct relationship between these two values as well. So which part is caused by the relationship, which is the unique relationship between yt minus 2 and yt, and which part is caused by R1? We don't know that, so that is why we go for the partial autocorrelation plot, partial ACF, which takes out the effect of R1. What partial ACF does is it's going to delete this part, and R2 will often be smaller, but whatever smaller R2 is left, that will be the unique relationship between yt minus 2 and yt, and not just be a reflection of R1. Because we want to see the unique relationship, not just a reflection of R1. So that's the ACF. Now let's see the partial correlation. So partial autocorrelation measures the strength of the relationship between current yt and yt minus k, the lagged value, when the effects of intermediate lags 1 to k minus 1 have been removed. This is useful because if simple autocorrelation of order 1 exists, like R1 exists, then this creates a relationship between yt and yt minus 2 as well. We just saw that I talked about how R1 creates R2. And so partial autocorrelation, we call it alpha. So alpha 1 is well, let's talk about alpha 2. Alpha 2 is going to be R2, okay, minus effect of R1, the effect of R1, okay? So that's going to be alpha 2, the partial autocorrelation at lag 2. So you're going to get the unique relationship between yt minus 2 and yt by partialing out or controlling for the effect of yt minus 1, the intermediate value. Again, it's going to be between plus and minus 1, and the significant values are going to be by the same formula. Okay, the partial autocorrelation function is just a plot of alpha 1, alpha 2, alpha 3. So let's look at an example that'll clarify. Okay. So here we have, for the same time series, we have the autocorrelation function plotted here. Do you see the decay? See the decay happening? And when it goes to negative again, it slowly comes back. So it's going to move down like a sinusoidal pattern, right? So sometimes you just see a decay like this, and sometimes you see a pattern like this. Okay, and usually, actually let me fix that. Usually when you do see the sinusoidal pattern, kind of gets smaller in magnitude as you go on. Okay, so you often see these types of autocorrelation function plots. Now let's make for the same time series, let's calculate the partial autocorrelation function. So at lag 1, this is at lag 1, they're both going to be equal. Alpha 1 equals R1 by definition, because there's nothing to control for you at lag 1. You have to control the intervening lags. Well, there's no intervening lag. Lag 0, there's no autocorrelation. That's just Y with Y. Lag 1 is the first autocorrelation. There's nothing between Y1 and any lag below Y1. Y1 is the smallest lag possible. So alpha 1 and R1 are the same. There's no controlling happening. But this is where the fun starts. So when you go to R2, so this is R2. This is being affected by R1. R1 is affecting R2. But when you partial out the effect of R2, you notice, oh, it's actually negative. Alpha 2 is actually negative. So let's say if this is sales data, if you had high sales in a month, the month after 1 month, you skip a month. So if you had high sales in March, you skip June. In July, you're going to have low sales. Maybe people advance buy or something, right? So the relationship at a lag of 2 is actually negative, and it is significant. It's below this line. See, these blue lines, this is plus 1.96 times square root of t. That's the length of the time series. This line is minus 1.96 times square root of t. And so you can look at the partial autocorrelation function and notice this actual negative relationship was made positive because of the influence of R1 or R2. But when we control for R1, we get the pure partial autocorrelation at level 2. And then we see at 4, right? And so on. Okay, so this is how you will often see much fewer strong values in the partial autocorrelation plot and a lot of positive or negative values in the autocorrelation plot, because ACF, one autocorrelation affects the other, which affects the other, which affects the other. But in partial, nothing affects anything else. Everything is the original autocorrelation between that lag, controlling for all the other lags in between. So that's all you need to know about autocorrelation and partial autocorrelation, because sometimes when you are fine-tuning a forecasting algorithm, you might look at these and say, oh, okay, there's not a lot of correlation over time, so that is why any method which only uses historical data is not working well. You can diagnose why a forecasting algorithm is not working well. Because if there was none of the partial autocorrelations were significant, then that means the past is not really telling you much about the future, right? Because there's no correlation between lagged values. So it's useful to know about them, and you can ask the software to plot these, just like I've shown you the plots, and you can look at them. Now let's get started into actual forecasting method. We're going to look at two main types of method: exponential smoothing and its modern version. The updated version of exponential smoothing is called ETS. They're very similar method. ETS is just, you can say, like an upgrade of exponential smoothing. And then we'll look at ARIMA modeling. So ETS and ARIMA, they're like the two very, very popular forecasting methods used in real life. Exponential smoothing is the historic, kind of classic version of ETS. And these are the two ones we're going to cover. Now, that's not the end of it. There are other more machine learning-based forecasting algorithms which we don't cover because we're only spending 1 week on advanced forecasting. If I did a whole course on advanced forecasting, you would cover those. But at least you need to know these, because a lot of ERP software will have ETS and ARIMA methods built in. A lot of supply chain planning software will have these methods built in. So if you're doing supply chain planning or you're in a role using software to do that, you need to know what these methods are and the basic logic behind them to be able to use the software successfully, to be able to read the documentation and so on and so forth. Okay. So the main idea behind exponential smoothing is averaging past observations to estimate some parameter of interest. So you may want to estimate the trend component by averaging past observations. The other main idea in exponential smoothing is that recent observations are more important than very distant in time observations. So if I'm sitting in September trying to forecast October, September, August, July, this recent data has more to say than data from 3 years ago. Okay, and so in all of these exponential smoothing and ETS methods, recent observations are given a higher weight than very distant observations. So essentially, the main idea you need to know, exponential smoothing captures the idea that the past has something to say about the future, number one. Number two, the recent past is more predictive of the future than the distant past. And number three, that by averaging stuff up, you can reduce noise or average out the noise, and you can have more stable or better estimates of whatever it is you want to estimate. So these are like the main key ideas behind these methods. So ETS, sometimes people just use ETS for exponential smoothing as well. ETS actually stands for error trend seasonal. These are the components of time series that ETS methods try to estimate. And as I mentioned, ETS are an upgrade or an update on exponential smoothing methods. So some people just use ETS to refer to ETS as well as exponential smoothing. They're both the same thing, just like updated exponential smoothing is ETS. And I'll show you what the difference between them is. ETS gives us some output that exponential smoothing cannot give us. Basically, exponential smoothing just gives us point forecasts, and ETS is able to give us prediction intervals. So remember I showed you a slide in part 1 of the lecture about the usefulness of prediction intervals, because point forecasts are almost always wrong. The actual value will be above or below the point forecast. And so exponential smoothing was limited. It could only give us point forecasts, but with ETS methods, we can get the prediction interval around the point forecast. So they're essentially the same thing, with the ETS being the upgraded version, which gives you the estimation prediction intervals as well. Okay, sometimes these methods are also called state space methods. ETS is another word for ETS is state space methods. And the main idea, why are they called state space methods? So, very easy idea, nothing complicated. As the name suggests, as the name suggests, we're going to track the trend and the seasonal component, and anything that's left over is called the remainder or the error. Remember time series decomposition? Why we had to understand that? Now it's coming useful, right? We decompose our time series to trend, seasonal, and then we had remainder, which can be called error. So we're going to track the same components. So the state is our current level of tracking these components. So at any given point in time, the state is our current estimate of the level. That's called L at time t. Okay, changes in L become the trend. Trend, this is the rate of change in L. How fast is L changing? Is L changing, is sales growing by 10 more units per week, or is sales growing by 20 more units per week, or 500 more units per week? What is the growth in sales? That's your trend. That's BT, the trend at time t. And if you remember from algebra, if you did algebra in high school or something, you often had the equation of a straight line, y is equal to mx plus c, or y is equal to a plus bt. So b or m are often the letters of the alphabet by convention used for slope or rate of growth. So that's why we just, his convention, we use B for trend. You could use T, you could use whatever you want to call it, but, historically the literature calls it B. So level is L, rate of change in level is B, and then the seasonal indices, different months or different quarters, how much are they above or below the mean? That's going to be captured by the S values. So whatever our most recent estimates of these level, trend, and seasonal indices are, that's the state of our system. Okay, based on this state, we can forecast the next value. So if we're at time t here, the state is at time t. We're using the state at time t to forecast the next value at time t plus 1. Okay, so we make our forecast for the next month. Then we observe, then a month passes, we observe the true value, right? We forecast the sales for October. When October finishes, we know the true sales value for October. Once we have the true value and we also saved our forecast, we can compute the error. Error is simply the difference between the true value and our forecast. That's the error. If the error was big, we need to update our state. If the error was very small, we might still update the state but make a very tiny update. So based on the error, we want to update our state. We want to say, our estimate of level and trend and seasonality was wrong, which is why our forecast was wrong. So let's update our estimate. So we update the state using certain equations based on the error, and we get a new level estimate, L of t plus 1, a new trend estimate, B of t plus 1, and a new seasonal indices estimate, S of t plus 1. Based on the state at time t plus 1, we can now generate a forecast for time t plus 2. So this state at time t plus 1 will now give us a forecast y hat of t plus 2. And then after that, we will observe the actual value at t plus 2 at some point. That will give us the error at time t plus 2, right? The error will just be y of t plus 2 minus y hat at t plus 2. Once we get the error, we can update the state again, and then we'll get the state at time t plus 2. So it's like this cycle which repeats. You have a state, you use the state to generate the forecast, you observe the true value, you have an error, use the error to update your state, then the next time period you go make a forecast again, observe the true value again, find the error, use the error to update the state, next forecast, the cycle repeats. So that's why they're called state space models, where the state keeps updating based on new observations of data. Okay. So all of this happens in exponential smoothing. This happens because when you're doing exponential smoothing, you are having estimates of these things and you are updating them. All of this happens in ETS, the upgraded methods. And so these types of methods are sometimes called state space or state methods of forecasting. Okay, so the same thing happens in these, both of them. Both of them are really the same thing. It's just, I told you, ETS is just the updated version of exponential smoothing. You can think of them as the same family, the same method. Just, remember we talked about time series decomposition. We said how we had X11 method, then we updated it to X12 and then X13. So X13 is just update on X12, X12 is just update on X11. Same thing, exponential smoothing are the classical methods. We upgraded them to ETS, basically the same thing, just added some bells and whistles to get ETS. Okay, so this is a family of methods. We're going to use some notation to identify which method in the family we're going to talk about. So, we're going to, whichever method we deploy, if we think there's no trend in our data and we want to deploy an ETS method or an exponential smoothing method that does not care about the trend, we're going to say N for trend. So we often call this like this, ETS, and then we have 3 letters to put. The first letter captures the trend. So if we feel there's no trend, we'll put N here. If we feel there is a trend, then we will do ETS method and we'll put A for trend. And if you want to dampen the trend, remember I talked about how there's this idea if you're forecasting several months in advance or several years in advance, if you have a spurt of growth right now, and remember all of these methods prioritize the recent past. If you had a spurt of growth, exponential smoothing, ETS methods will say, oh, trend is going through the roof, but maybe you suspect this spurt of growth is not going to last forever. So maybe you want to dampen the trend after the next prediction. So you want to do prediction for time period, the next time period using almost all of the trend component, but then the period after that, you want to dampen it. You want to reduce the trend component. And the period after you want to dampen the trend, then you'll use an additive damped trend, AD. So then you'll call your ETS method with the first value being AD. Okay. Now, the second method, the second value is going to be about seasonality. Do you have seasonality? If you have no seasonality, you will say, well, I have no seasonality, N. If you have seasonality, you can do additive or multiplicative models. So you can do A or you can do M. Okay. And then the last one actually is for ETS. So exponential smoothing, you just have these two. So let me show you. Okay, so you just have two. Trend NA or D or seasonality NA or M. You don't have this third, you don't have this for exponential smoothing. Okay, so for exponential smoothing, you just say exponential smoothing, okay, with N and N. Or you'll say exponential smoothing with A trend and then additive seasonality, or A and M, like that. But ETS method will have a third term, okay, and what will be that third term? That will be the error term, okay. So for ETS methods, you can have an additive error, A, or a multiplicative error, okay. So the error term is explicitly modeled in ETS methods. That's the upgrade over exponential smoothing, because once you model the error term and the error is normally distributed and random and independent, then you can make a prediction interval. Just like in statistics, you have a confidence interval. The confidence interval requires some variability estimate. The higher the variability, the bigger the confidence interval. Same idea. You want to estimate the error variability and use the error variability to estimate your prediction interval. And so you can model the error in two ways, as an additive error or a multiplicative error. So the third term for ETS models is whether the error is additive or multiplicative. Okay. So let's look at our exponential smoothing models. Okay. So these are the equations. You don't have to memorize these equations. You don't have to know these equations. I'm just giving you as documentation that you can have these equations. Software will do all this for you, but you just need to understand the logic, which I can show you through these equations. Okay, so let me show you. When you have no trend and you have no, this is no trend, and you have no seasonality, NN. So this will be exponential smoothing, EXP smoothing. NN. That's the method. That's your simple exponential smoothing you have already covered in some operations course, where you just take y of t equals alpha, y of t plus 1 minus alpha, and the previous forecast, okay? So we just have the level component. If you look at time series decomposition, if you look at your state has level, but no trend and no seasonal indices, okay? For NN, no trend, no seasonality, okay? Okay, so that's your simple exponential smoothing. Now, if you do have additive trend, but no seasonality, so that will be an exponential smoothing model with additive trend A, but no seasonality N. That is called the Holtz method. You've probably studied it in some courses. Very simple. Is you have two equations, one to model the level and another to track the change in the level. Right, and your forecast is going to be the sum of whatever components you have. So now you have level plus trend. So you combine the two to develop your forecast. Here you just had level. So you can see this theme, your forecast is always going to be combination of all of the components you're tracking. You're tracking level and seasonality here. You are tracking level, trend, and seasonality here, level, trend, and seasonality here. So whichever components you're tracking, which is given by these values NA, NAM, those are the components you'll combine to develop your forecast. So if you have just an additive trend or additive damped trend, these are called the Holtz method or Holtz method with damped trend. Okay, so this box here has the Holtz equations, this has the Holtz with damped trend. If you have both, so you have trend and seasonality. So here you have additive trend and additive seasonality, AA, and here you have additive trend and multiplicative seasonality. This is called Holtz-Winters method, and this is also called Holtz-Winters method with multiplicative seasonality. Okay. And then this would be Holtz-Winter method with a damped trend. So same thing, Holtz-Winter with damped trend, Holtz-Winter with damped trend. Okay, and this with just seasonality and no trend, this is called just the Winters method. Winters alone. Because Winters came up with exponential smoothing for seasonality, Holt came up with exponential smoothing for trend. So if you only have trend, you have the Holtz method. You only have seasonality, you have the Winters method. You have both trend and seasonality, you have the Holt-Winters method. Easy peasy, lemon squeezy, done. That's all you need to know. That you could have no trend or additive trend or damped additive trend, NA or AD. You could have no seasonality, additive seasonality or multiplicative seasonality. Whenever you have trend, A or AD, that's some variation of the Holtz method. Whenever you have seasonality, A or M, that's some variation of the Winters method. If you have both trend and seasonality, AM, ADA, ADM, all these combinations, you have Holt-Winters method, some variation of the Holt-Winters method. In terms of the equation, this phi, you'll only see this phi in the damped trend equation. So down here, is where you'll see the phi. That's the damping factor, and almost always it's kept between these values because that keeps things stable. You don't want it to be too low, too much damping, or too high, too close to 1. 1 would mean like no damping. Okay, so we almost practical experience tells us it's almost always going to be between these values. That's your damping coefficient. And then M is the number of observations within one cycle of your seasonality. So monthly data, M is 12, quarterly data, M is 4, days of the week data, Monday to Sunday, M is 7. H is how many periods ahead you're forecasting. Forecasting the next time period is T plus 1, so H is 1. Forecasting 2 time periods ahead is T plus 2, so H is 2. Forecasting 3 time periods ahead is T plus 3, so H is 3. So all this simple stuff, right? So you don't have to know the equations, but you have to know, okay, Holt's method handles the trend, Winters handles seasonality, Holt's Winters handles seasonality together, and this is how we, and you have to know these, that trend is N, A, or AD, seasonality is N, A, or M, and we can write this as exponential smoothing. Okay, or you can write it as ETS, we could put exponential here, and in brackets you'll specify, okay, if you're doing this method here, there's going to be A for trend and A for seasonality, so you write A, comma A. So that tells you which variation of the forecasting method you're using. As we will talk about later on in automated forecasting, with automated forecasting, the computer software will try all of these methods and select the best one for you. No, you don't even have to specify exactly which one. You can just tell the computer, try all of them and pick me the best one. Okay, because you have ETS versions of these methods where you can do testing to select the best model. With these models, there's no you can't select the best model by looking at things like MAPE. Okay, mean absolute percentage error, MAD, mean absolute deviation. These are forecasting errors, right? So in some basic forecasting lecture or topic, you'd have studied them. Or you can do cross-validation. We'll talk about that towards the end of this lecture, which is cross-validation. So you can use these things to select the best method. But let's say, exponential smoothing with additive trend and multiplicative seasonality gives you a MAPE of 12%. And exponential smoothing with no trend and just additive seasonality gives you a MAPE of 11.5%. So which method you should select? Now, no trend has fewer parameters. It's a more parsimonious model, and MAPE is almost the same. So should you go for the more parsimonious model or this model? There's no way to test if the added complexity of adding the trend is worth it. There's no statistical test. I mean, you can kind of mentally make a judgment. You can say, oh, 0.5% error, what is the cost to me of being 0.5% more accurate? Am I offering the data or not? You can make some judgment call, but there's no statistical test to see if the parsimony is worth it. Whereas with ETS models, we'll have a statistical way to say, oh, whether we want to go for the more parsimonious model or not. Anyway, so this is exponential smoothing. Okay. Let's go on. This is a good example. We have annual data over the years. So annual data means what? There's going to be no seasonality, right? Because seasonality is when you have data at a finer time grain level than a year, because seasonality is over the months or quarters or days of the week, right? Or weeks. When you have annual data, there's no seasonality. So annual data means no seasonality by definition, which means no Winters method. We can't use Winters methods or Holt Winters. We're just going to use Holt's. So if you just use Holt's, you can see there's a sharp trend here. So your forecast is going to grow a lot for the next 5 years. This is a 5-year forecast, right? 5 years, showing a lot of growth. But you might say, well, good things don't last. This spurt of growth is not going to last. So you might want to try it with the damped Holt's method, not just the Holt's method. So if you dampen the trend, you can see how the forecast dampens as you go forward in time, right? It brings this forecast down, the dampening effect. That's the phi parameter in your equations, bringing your forecast down. And so that's how the damped trend forecasting kind of looks like. It dampens the forecast downwards. Because what people have found practically is if you have a strong trend and you're forecasting multiple years in the future, strong trends will often not last multiple years into the future. So it's conservative to use damped trend to not be too optimistic for far out into the future. Okay. Okay, now let's look at ETS. What did ETS do that made them so nice that now we almost always just use ETS? We don't use exponential smoothing. Well, ETS, also called state space models, again, I told you why, to track the state of L and trend B and seasonality S. They define an error term. You don't have to remember the equation, but basically it's the error we'll be seeing all the time. Remember, error is just the difference between the true value. This is the true value. And this is the forecast. Y hat is always a forecast, right? The difference between them is the error or the unexplained variability, okay? And you can also find a version of the error by dividing. This is the error used in MAPE. So actually, let me write it carefully. This is the error you use in your MAD calculation, mean absolute deviation, or your average error calculation. You use this yt minus y hat t. Okay, the actual value at time t and the forecast for time t. This forecast was developed using data till time t minus 1. That's what is given t minus 1 data. Okay, but for MAPE, we use fractional error. Okay, error was 20%. I was 20% off. I was 10% off. I was 30% off the true value. So these fractional errors are what you use for MAPE. So there's two ways to define errors in forecasting. Either as a fraction, I was off by 10%, 20%, or as an absolute value, I was off by 500 units, 50 units, minus 50, plus 30, right? So you can have the actual value plus minus actual value, or you could have a fraction. So the actual value is called additive error, and the fraction value is called multiplicative error. And if you like MAPE, you might like this, and if you like MAD, you might like this. Okay, so we have a choice. So in ETS, the first choice is the same as before, additive trend or no trend or additive damped trend. The second choice is, multiplicative seasonality, additive seasonality, whatever we choose. And the third choice is you want an additive error or a multiplicative error. So the third choice for the error, you can either have A here or you can have M here, one of the two in your ETS method. Okay. So ETS is the error term is assumed to be independent, normally distributed with constant variance sigma squared. So the variance of the error doesn't change with time. Exponential smoothing models are rewritten using the error term. So you go back to these equations, you do a bunch of algebra to rewrite them in terms of ET. And so in ETS equations, you get ET in these equations, and some of these things change to incorporate the ET. Basically, just do algebra to rephrase these in terms of ET, the error term ET. Okay, then models are estimated using maximum likelihood algorithms, and these algorithms can choose the values of phi, all of these values, all of these constants in these parameters like alpha, beta, gamma, and starting values. You need initialization values. For exponential smoothing, you kind of have to estimate them yourself, or the algorithm will estimate them using some rule of the thumb. Here, you can use maximum likelihood algorithms to estimate the starting values and those parameter values to be the best, the optimal values. So that's an advantage as well. Okay. So what are the advantages of ETS methods? They can compute prediction intervals, not just point forecasts. Can use information criteria, AIC-C or AIC values, to select the most appropriate model for a given time series. Just give a time series to the computer algorithm, the software. It will use maximum likelihood to estimate your ETS algorithms. It will try all of them. And then it will say, oh, this algorithm works the best. Right? It'll use AIC adjusted, which is the AIC with a small c, AIC-C or AIC values to select the best method. Almost always you want to select the method which has the lowest AIC-C value. This the small c is a correction for small sample size. Because if you use AIC values and you have don't have too many observations, that can mislead you. So you want to use AIC-C almost always, basically always, small sample sizes. Okay, so whichever ETS method gives you the smallest AIC value, that's pretty much like the best. Okay. When using MAPE or MAD, that you have to use for exponential smoothing because there's no AIC value for exponential smoothing. So for exponential smoothing, you can select the best method using MAPE or MAD, but there is a chance you might overfit the model because more complex model with more terms, more damping, seasonality, trend, everything, the kitchen sink thrown in, will tend to give you lower MAP and MAD and MAP, right? MAD and MAP. Whereas sometimes a more parsimonious model may be almost as good, but just a slight reduction in model fit. And you don't want to overfit because overfitting means your future predictions for unseen data can be wrong. And so this problem is decreased in ETS method because ASC will prefer a parsimonial model as long as model fit is not significantly compromised. Okay, so if you're given a choice, if your software supports, just use ETS methods. Forget exponential smoothing. That's the old stuff because you're going to get a lot of benefits. You're going to get AICC is going to pick the best model for you, pick the best ETS model for your time series, and the computer software will pick the best ETS model for each product you have. If you're going to forecast for 50 products, it'll apply all the ETS algorithms to each product, see which one has the smallest AICC, and pick the best one for each product, right? It will give you prediction intervals, not just point forecast. So prediction intervals on top of the point forecast plus the point forecast. Okay. Right. And it has a less chance of overfitting, the data. Overfitting means you're trying to fit to the noise, not the signal. So you're trying to fit the past values exactly, like 2 exactly, and the noise that's not going to be repeated in future, you overfit that, and then your predictions are not that correct. Less chance of overfitting to the data. So because of these advantages, most people use ETS if the software supports it. For ETS, because you can have trend, right? So you can have no trend or dampened trend, or you can have no seasonality, additive seasonality, and multiplicative seasonality. Then on top of that, you can have additive error or multiplicative error. Okay, so let me correct myself. I made a tiny mistake. Okay, ETS. Remember, ETS, what it stands for? Error, trend, and seasonality. Okay, and seasonality. So in brackets, the first term is the error. So it's going to be A or M, additive or multiplicative. See, A means additive error, and M means multiplicative error, the fractional error. Okay, and then the second term is going to be trend. So that's going to be NA or AD, not M, N or A or AD. And the third term is going to be seasonality, which is going to be N or A or M. Okay, and so the first term is the error, which is additive error is going to be all A's. Okay, and for multiplicative error, the first term is going to be all M's. So remember, ETS, the order is this: error, trend, seasonality. So the first variable is going to reflect the error. So this you have to know, like for ETS, like I'm giving you this right here. So if I tell you, okay, I did this forecast using ETS MAA, so what was my error? You'll say, oh, M, multiplicative error. Did I have trend? Yes, you had additive trend, but not dampened trend. It's not AD. Did I have seasonality? Yes, you had additive seasonality. Okay, so you need to be able to know. So these A and M are the options for the error term. NAAD are the options for the trend part, and N, no trend, additive trend, or multiplicative, no seasonality, additive seasonality, and multiplicative seasonality are the options for the seasonality part. Okay, and so you get 9 and 9, 18 models. However, of the 18 models, these 3 models with additive error but multiplicative seasonality are not used, are not recommended to be used. I mean, you could try to use them because sometimes they're not numerically stable, especially if you have very small sales value sometimes, or zero sales, if you have zeros in the data, or small values. Sometimes the multiplicative seasonality, the seasonal index becomes close to 0, and because you divide by it, your estimates blow up. So sometimes these are not numerically stable, because if you look at the equations, here, see, multiplicative seasonality. See, you divide by the seasonal index here. See? You see this division? And if S is a very small number going to 0, this division causes this to blow up to infinity, right? Because when you divide by 0, you get infinity, right? So if you have very small sales value or zeros in your data, sometimes S becomes 0 or close to 0, and that destroys your forecasting because of the division by 0 issue, okay? So oftentimes people don't like to use multiplicative seasonality for that reason, okay? And so these 6 and the bottom 9, these 15, I guess if you look at what's left, you're left with 15 variations. So the 15 variations of ETS method are what are commonly used, and the software will automatically pick the best one for each time series you give it based on what? Based on AICC. So you should know if I give you, okay, what is ETS, additive error, no trend, additive seasonality. So you should be able to interpret what these terms mean. You should know that AICC is what we use to pick the best model. The smaller the AICC, the better the model we have. Okay. Okay. So let me show you some examples where ETS was used. Notice the cool thing about these examples. Yay, we get prediction intervals. We love prediction intervals. Okay. Notice the prediction intervals, right? And so here you have data with trend but no seasonality. So look at that. Multiplicative error, that's the error, M for the error. Additive trend, and no seasonality. No. Why no seasonality? Because I have annual data. See at the bottom, this is annual data. Whenever you have annual data, you can't have seasonality. Seasonality is always has a cycle over 1 year or less than 1 year. So if you have just one observation per year, how are you going to detect a cycle if you have only one observation per year? There can be no seasonality when you have one observation per year. So annual data has no seasonality, okay? And so we just use error and trend, and we got our prediction. These are our point forecast, this black line. This is the point forecast. It gives us the point forecast as well as the prediction interval. Now let's look at something with seasonality. Now this one has no trend because if you look at long term, you're going up and around the same average, approximately the same average. There's no really real trend. But we do have a lot of seasonality, so we did additive seasonality. And you can see the prediction. So the point estimates are the blue line here. This blue line, right? This line, that's the point estimate. And then these blue bands are the prediction intervals. So we got prediction interval and we get the point forecast from ETS methods. This is awesome. It does very well. If you have a graduate degree in supply chain management, you have to understand ETS forecasting. A lot of software will do it for you. It's very useful. It's very practical. You can automate it, run on many time series. It uses AICC to select the best model for each time series. Gives you the forecast. Gives you prediction interval. Problem solved. Okay. So at this point, you should pat yourselves on the back because you've learned a professional industry level forecasting, the theory behind a professional industry level forecasting algorithm, the ETS one. Now we're going to go to ARIMA models. Okay.